Hello, this is the next video in a playlist that I'm calling Complex Variables, and we're in the complex numbers part of this complex variables playlist. Let's jump to today's topic, which is a complex conjugate, and then we'll move into the equation for a circle in the complex plane. As a reminder, the conjugate, also called the complex conjugate of a complex number z, which is a plus bi. The conjugate denotes, has the bar above the z is equal to a minus bi. Let's look at some properties, and then what follows, we're going to let z1 and z2 be generically these complex numbers, a plus bi and c plus di. Now let's prove that the complex conjugate of z plus z2 is equal to the sum of the complex conjugates. So let's look at that. z1 plus z2 conjugate. Let's plug in what, let's first of all add the complex numbers. So you add the real components, add the imaginary components, take its conjugate, which means change the sign, and then we're going to rearrange the bi. We're going to move it to, to the a and then the di. Well, those are the complex conjugates of z1 and z2 respectively, and that's what we wanted to show. Next, let's show that the conjugate of the product of two complex numbers is equal to the product of the conjugates of those two complex numbers. Well, let's look at it. Z1, Z2 conjugate. Let's plug in what Z1 and Z2 are. And in the first video, we showed how to multiply two complex numbers, and that's what this piece here is. Now, to take the conjugate, we change the sign. So this is the conjugate. And then this, we can factor it. And if you, with a little bit of work, you can show that it's this product of two complex numbers. Well, this is the complex conjugate of Z1, and this is the complex conjugate of Z2. So this is what we wanted to show. Now, next, let's show how to grab the real component of a complex number by using this formula, Z plus the conjugate of Z divided by 2. So let's look at that. Well, we plug in what each of those are, a plus bi plus a minus bi. And then when you add complex numbers, the imaginary piece goes to 0. And we're left with 2a over 2, which is a, which is just the real component of the complex number. And that's what we wanted to show. Now, to grab the imaginary component of a complex number, you can use this formula. And these are going to help when we look at the equation of a circle. So let's evaluate this expression. So z minus the conjugate of z divided by 2i. Plug in what the values, the complex numbers and the conjugate of the complex numbers. Notice that the a's go away, and then we're left with 2bi divided by 2i. Well, that's b, but that's just the imaginary component of the complex number, and that's what we wanted to show. Now, in what follows, to me, it's helpful to describe the complex number as x plus yi. When we're converting from the xy plane to the complex plane, it's just easier for me to think about it like this. So in what follows, this is the new general form of the complex number. And we want to prove that the equation of any circle in the z plane can be written in this form. Alpha times this product, beta times z, the conjugate of beta times conjugate of z plus gamma, it's equal to 0. Alpha and gamma are real numbers, they're constants. Beta is also a constant, but it's a complex constant. And then beta bar is the conjugate of beta. Now, for me, it's easier to go in reverse. I want to start with the general equation of a circle in an xy plane, and then it's easily shown that this is the general form of a circle. And then using the previous two problems where we grab the imaginary component and the real component, we get this expression. Okay. So, of course, the 0 equal a comes down, a squared plus y squared. That is easily shown to be z times the conjugate of z. and I'll leave that for you. But then x is the real component of the complex number, so we can plug this formula in that we showed previously. Y is the imaginary component of the complex number, and we prove that it's this. Now let's gather like terms. We want to gather the z and then the conjugate of z, right? And so we get this. Notice that this z has a c and a 2i under it, which is this, and this z has a beta, a b over 2. Anyway, but this is it. This is the form we wanted to show. So if we let a be alpha, and this is beta, right? And then its complex conjugate is this, and so this is it. So this is the general form of a circle in the complex plane. Now, quickly, let's look at some examples. Oh, and before we go, one note, without this product, the alpha term, then we get lines in the complex plane, and then we'll show that. So z conjugate times the conjugate of z equals 16. This right here is x squared plus y squared equals 16, and that's a circle centered at the origin 0, 0, which is this. But this is a circle centered at the origin in the complex plane with a radius of 4. If we look at this expression, z plus conjugate is equal 4, and then we expand, we put in x plus yi, and then this conjugate, and that simplifies to x equal 2, which is a vertical line. So this is a vertical line in the complex plane. And to me, that's kind of cool to think about. Z bar, or the conjugate of z, is equal to z plus 6i. When we subtract the conjugate over and then simplify it, this simplifies to y equals minus 3. And I'll let you do the math there. But this expression is a horizontal line in the complex plane. This is a vertical line, this is a horizontal line at y equal minus 3. And also kind of cool for me to think about. Let's show some of these properties are true using R. Now, when we enter complex numbers in R, using R, we can use the function complex, and this is really a simple use of it. It has more functionality, but you just say real 3, imaginary 4, and it creates an imaginary number stored in Z1. You can also just enter it directly into Z2, where minus 2 plus 2i, and it just knows that it's a complex number. So if we look at the conjugate of the sum, that's the sum of the conjugates, and notice that it's the same, 1 minus 6i in both cases. The conjugate of the product is a product of the conjugates, and this number is minus 14 2i, and then the product of the conjugates is the same, as it should be. We proved that it has to be. Now to grab I want to show you at Z1, 3 plus 4i. So to grab the real component, use this formula, and notice that it is 3 plus 0i, which is the real number 3, but R tries to keep that in, the complex form. If we just grab the real component of this, of course it's 3. And here is the formula for the imaginary component of a complex number. And notice, so I'm dividing by 2i, the complex imaginary equal 2. So this is 2i. And this is Z1, minus the conjugate Z1, which is 4. It's the real number 4, which is the imaginary component of Z1. Okay, well, that's all I have for this video. Let's see what we're going to look at the modulus of complex numbers in the next video. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.